5. Welcome to Northwest Nuclear Laboratories live, and so we're going to be doing some adventures in grassroots production for the next few weeks, and there's going to be some false starts and some learning. We have a lot of equipment, and so it's more like flying the control panel of a 747 rather than a Cessna. This isn't trying to do television over your telephone. So anyway, we have some really exciting stuff that we're going to be looking at tonight, and I hope that through the course of the evening that you get a chance to do some things that you haven't done before. We are going to be having interviews for some of our new folks tonight. So Adam is going to be teaching a class in the reactor room. We're going to televise that class, so it's directly following this production. We will switch to the reactor room, and Adam will come in, and we'll have a live audience there. A couple of things about the live audience. You need to be aware that there's a camera in the room, and standing directly between the camera and the reactor is not a good thing. So be aware of where your head is in relationship to the camera. Think of the camera as another person who's looking over your shoulder, trying to see the instructor, trying to see what's going on. So we're going to kind of share that experience. So Northwest Nuclear Laboratories is dedicated to inspiring, empowering, and ultimately marketing young people to the tech sector. We're getting really good at that. And after 7 years and $800,000 in scholarships and a bunch of fine young people in the tech sector already, it's time for us to go out the window, if you will, and let the rest of the world share some of this magic. So that's what this is all about. Streaming a television show from a live laboratory. The thing is about live science is it doesn't always work the way you expect it to, and since it's not rehearsed, and since you can't go back and redo it and cut out the part that went wrong, you'll get a chance to see it as it really happened, play by play, blow by blow. I'm just as excited to see what that looks like as the next person. So tonight, couple things. We are starting the meeting at 7 o'clock promptly. Try to be here at 7 o'clock because we will be rolling tape. We will be pushing the stream out the door, and we have some ground to cover, so appreciate it if you can show up a few minutes actually before 7 o'clock so that you're in your seat by the time we actually push the button. Tonight's a special night for me because one of the things I love to do most is recognize somebody who has done a spectacular job. And we're going to do that tonight. So Michaela, will you come on up here? Now there is a tradition here that goes back a ways. Jake was our first super brain, and he inspired this tradition, and he came in here and did some amazing things, and they were so amazing that I said, you know, I'm not really sure who's teaching who anymore. So in that level of confusion, I decided it's nuts for him to go another year as a student when Jake is spending most of his time being an instructor. Well, we have that in you now, and it's clear. Not only have you accomplished some amazing things as a scientist and taken several projects over the course of your time here, not only to the Washington State Science Fair, but all the way to the International Science Fair. Huge recognition, first place recognition in category. So we would like you to be able to teach here during this next year as you figure out what you're going to be doing in your senior year to go beyond what you're already doing. Now, I would like to point out that she's a high school student working for Boeing and also working for a laboratory up in Ballard. What's the name of that laboratory? LabCorp. Working on electron microscopes and developing a proficiency that's nothing short of professional. So it kind of follows that we'd love to learn some of the things that you're now learning, so please feel free to share those. This is your ticket from us. You have graduated from our curriculum, and we welcome you now as an instructor. Thank you. So we're going to have some application forms that new people need to fill out tonight. So if things get busy and confusing, just know that I need to get these application forms filled out before you leave. You can get them from Lynn. So, yeah, redundant. We're conducting interviews this week. I am going to pose an interesting question tonight. We're going to talk a little bit about what a scientist is. Could you pull that table over? No. That's fine. A scientist is someone who creates new truth. Now, this is a statement that we're going to fiercely defend as an organization and as a group of scientists. If I said there's no such thing as truth, and there are active philosophies and perspectives that talk about truth, but I were to say it in a court of law, could the legal system work without truth? We'd run into a real problem. So if we were to go into the area of science and not be able to identify something that is true versus something that is not true, we couldn't learn anything. We couldn't draw any conclusions. So we can create new knowledge, but truth is something that comes about when we take the evidence, look at the results, see that they're repeatable, reliable, draw on our peer review, and we come to the point in time when a theory graduates and becomes truth. Now, does that mean it will always be true? Well, was the world always flat? No, we've blown it a few times. Man cannot go faster than the speed of sound. It is absolutely impossible. It will never happen. Oh, yes, it did. So John Glenn took the X15 and proved us all wrong. Those kinds of things happen. But what I want to emphasize is that truth comes about through something called the scientific method. We'll be going into the scientific method in a few minutes, digging down into what it is. But before we do, I'm going to ask the question, is that all a scientist does? No, he's a guardian of truth. And this isn't talked about in a lot of courses. It isn't dealt with in a lot of courses, but you can darn well bet we're going to deal with it here. Why is it important? Profit corrupts truth. Big companies making big money will buy scientific results to sell their products and push their profits. This kind of science, unfortunately, undermines the scientific reputation of the work you're doing. It undermines our credibility as scientists. And we need to be fiercely opposed to those kinds of practices. We need to recognize that when we become a scientist, the most important thing that each one of us has is not our skill and ability to do science. It's not being smarter than Einstein. It's our integrity. Because if we lose our integrity, then we've lost the right to represent the scientific community and truth as a whole. More than once, scientists down through the ages have become infamous because they sold out their reputation for the profits and the popularity of a discovery that was ill-formed and unresearched. So, we have something called the scientific method. And up here, we start by asking a question. And then we do some background research. And we ultimately arrive at constructing a hypothesis. Next, we test using an experiment that we've designed. And if that process works, if that experiment works, then we can analyze the data and draw some conclusions. If it doesn't work, then we're going to come out here and we're going to loop back up and we're going to fix our experiment. Ultimately, we're going to publish our results. If our hypothesis is correct or incorrect isn't the point. The vast majority of the experiments you will do as a scientist will wind up being incorrect relative to your hypothesis. Edison did over 1,000 experiments trying to create a light bulb. They were all wrong. He finally did the one that was right. He finally found the material in the form of tungsten that would stand up to the heat and the gases that were still inside that bulb and allow it to last long enough to make light bulbs practical. Now, since then, a great deal has happened to the light bulb, but Edison's process of going back, analyzing what he did, and correcting it, the scientific method is with us today. And what we're going to ask you to do is embrace the scientific method and build a scientific reputation with it. This costs time, lots of time. If you thought being a scientist is easy, I have a whole different story. It's staying up late at night, reading lots of periodicals, doing lots of web searches, finding out that there is a level of granularity to what you're reading, and you're really digging down around the roots of things, trying to read between the lines, asking, did he really look at this aspect or that aspect? Does this answer really incorporate the information I need to predicate a hypothesis on? Or should I do some additional experiments to establish a foundation for my hypothesis? It costs a great deal of hard work to be a good scientist. And it can be compromised very quickly. Now, I've talked about corruption, but another way that you can compromise the integrity of your science and the reputation that you have as a scientist is by doing sloppy work. Your notes that you keep prior to conducting the experiment are terribly, terribly important. The settings of the dials, the settings of the machine, over and over again, scientists get in a haze where they're redoing experiments, but because they don't have a procedure and a checklist, and they're not double checking every one of their settings, they're getting crazy results and going back and trying to remember what they were doing by hand, and they lose track of what they got in the last 3 tests, and pretty soon the whole experiment is so muddled they can't even tell where they started, much less whether the results they have mean anything. Sloppy science can bite you. So we learn to be meticulous. We learn to pay attention to detail. We learn to document. Very, very important stuff. The science fairs, one of the privileges I have is being a judge. And I have come down the tables and I find a young person with copious notes, 3-ring binder, it's 4 inches thick, every conceivable experiment, well documented, well written up. And you can feel the integrity of the data this person has collected because you can see they are consistently meticulous. And even if they didn't achieve a successful experiment in that their hypothesis wasn't verified, that moment when they understand that they're being offered a job because they've been seen to be somebody that can be trusted because they are detailed and they are meticulous, pays off better than if they had succeeded in their experiment. Okay, so how do I create truth? Well, the way you conduct your science has to be done with a design of experiment. When you do an experiment, seek peer review. get some buy-in from some of the other people. Say, I'm trying to find out if this is true, and I need to know if you would go about it the same way, or if there's anyone else that's ever done this before who could give me some advice about how to set this experiment up. And oh yeah, I want to make sure the controls and the standards and the calibrations that I use add authenticity and integrity to the data, so that when I'm done with all this work that I'm doing, it will be useful regardless of the outcome. So the second thing you want to do is make sure that your records have a pedigree, that you can trace back in your process where all the variables are coming from, and that you can demonstrate that you didn't lose track of anything. Lots of times people don't label the bottles. They have a whole bunch of test tubes in a rack. They're working with clear liquids. They're doing dilutions. They're busy pipetting. And all of a sudden they discover they've got an extra row, and they're going, when did that happen? I don't remember doing that. What are these tubes, and what do they have in them? And all of a sudden the whole thing is trashed, and they've got to start over because they lost track. So having a pedigree to your experiments, having a pedigree to your calibrations and your standards, very, very important. There's a right way and a wrong way to publish the results of your science. Don't publish in the Globe. The National Enquirer is not a place you should make a scientific announcement. If you intend to maintain your scientific reputation, there are periodicals and scientific journals and places to produce your results. But the internet, and especially Facebook, is not the right place. Do not publish scientific results that mean a great deal to you on social media. That's not where they belong. Let somebody else do that. Let somebody else misquote you. You go ahead and make sure that you've got all the information properly put together, and then put it up in a white paper and publish it to a noteworthy scientific journal. And you'll achieve the credibility that you want so badly, and the industry will respect your results. Last of all, it's your responsibility to remember how to teach the science you do. All along the way, giving back is part of the scientific journey. Turning around and helping somebody come along behind you is important. You're going to have some tremendous scientific experiences. You're going to get to go some places other people don't get to go. You're going to get to perform some experiments somebody else didn't get to perform. They may be better than you. They may have more years as a scientist than you, but they didn't get to do the thing you got to do. And they want to have your help. They want to know how to do what you have done. That's cool. And so I found through the years that professional collaboration and working with other scientists, no one's really keeping track of who the great scientist in the room is. Things get very, very level, and people are all working together towards a common end. And if you have some knowledge that plays into this particular part of the research, because you happen to have been someplace someone else hasn't, you get to share it. You get to teach it. Don't charge people for sharing your science. Be generous. As you share your experiences, share your knowledge, yes, people will come to you more often and ask more questions. And sometimes that'll be kind of bothersome. But they also come and they share their successes and they share their stories. And you develop friendships and you collaborate. A scientist who's afraid that someone's going to steal their invention and who is afraid to share the research they're doing very often winds up in a dark corner without enough collaboration to get the job done. But people who can work together as team science, they can do things that very often nobody else can do. A team can always go farther than the individual, and corporations are banking on that today. You will be evaluated during the interview in your ability to do team science and to work together with other scientists and collaborate on your ideas. And yeah, you may, unfortunately, once or twice in your career, hear somebody else claiming one of your ideas. Oh well. No one said life is fair, but it is rewarding. And people that work hard will always be rewarded. And it's far better, I can tell you from experience, to share your information, be open and honest with your fellow scientists, be approachable, don't be condescending, don't be arrogant, and respect the new students as they come along and treat their ideas with respect. You'll make friends quickly. Allow dissent. That's an important one. If somebody doesn't like your idea, oh well. If somebody thinks that you went about it the wrong way, oh well. You're accountable to your own conscience. If they were right about their criticism, be quick to acknowledge it. If you don't believe they were, respectfully disagree and continue with what you were doing. You'll have critics throughout your journey. That's part of life. Don't take it personally. Don't be touchy. Science is a good place to develop thick skin. In the end, somebody who is persistent will be successful. Now I want to talk about the value of a failed hypothesis. I said there's a lot of people who make mistakes in their original analysis, and they create hypothesis and run the experiment and discover, nope, it's not going to work. So they never publish the finding because they're afraid that people will think bad of them because it didn't work. That's a disservice to the scientific community. Because you see, you nailed one reason it wouldn't work. That's valuable. That's huge. So here's an opportunity to give back. You put a lot of time and effort into that experiment, publish the result. Make it clear it bombed. And highlight your assumption in how you reached it that was in error, so that somebody else won't trip over the same stair you did. I have worked for companies where we were doing research and development on products and suddenly realized that we had tried to develop that same product 2 years earlier and it didn't work that time either. And here we are, $600,000 into this research, and we're working on a dead elephant. Why? Because nobody left a trail. Nobody published the outcome. They just canned the project and swept it off the table so that no one would see who was involved in the failed project. That doesn't do the company a lot of good. That doesn't do the future scientists a lot of good. So mistakes are every bit as valuable as successes. Think about it. Think about your part in contributing. Bad and good alike are valuable. Okay, we're going to do a couple of things tonight. We've got a video that we're going to be running in here. We're also going to be doing some interviews, and so we're going to cut it off at this point with the live broadcast. No, actually, no. We're going to keep the live broadcast going. We're going to the reactor room, and Adam, why don't you pick it up from there? Wing it. So while we're waiting for Adam to get to the reactor room, she'll bring it up.
Okay. And then microphone. Okay. Hello. Let's see here. There, I'm right now. So behind me, we've got the nuclear reactor that the students here at Northwest Nuclear Laboratories have built over the past years. The reactor slams ions of deuterium, which is a special form of hydrogen, together, and slamming those ions together, we are able to perform a nuclear reaction. You have chemical reactions, you have nuclear reactions. We're doing nuclear in this case. Keep going. So all of the magic is actually happening underneath the shield, so you can't really see what's going on right now besides through this little viewport right here. But to ionize the gas, we take the gas, we expose it to a really, really high voltage. In this case, we're running at 40,000 volts, so we can go all the way up to 80,000 volts. And with that high voltage and the ionized gas, we can accelerate the ions together. And the ions get accelerated, when they're fast enough, they'll slam into each other. And the reason they have to get going fast is that the nucleus of two ions really does not want to get close to each other. Like they don't want to touch. So to get them to do that, they have to have enough energy to overcome that repulsion force. So that's what the high voltage there is. Overcome the repulsion force, get the ions going fast enough so they can slam together, and then once they pass a certain point, then an attraction force takes over. And that attraction force attracts the ions the last little bit of the way together, and then they get combined from deuterium. They'll turn into a couple of different things. Most commonly, we're turning into helium, although it is possible that it can also be turned into tritium. Because if you think about it, we're using deuterium, so one neutron, one proton, because that's the isotope of hydrogen is. Hydrogen's one proton, deuterium's one proton, one neutron. You take those together, you slam them together, and you've got two protons that have got to do something. A lot of the time, you're going to end up with the helium coming off that, because helium has two protons. So when you form that helium, you get helium with two protons, one neutron, and so remember, we started out with two protons, two neutrons. Now we have a helium with two protons, one neutron. So the other neutron is given off as radiation. And so that radiation is what we see coming out of the reactor vessel in here. So if you look over here, you can see that this is a graph of the radiation output of the reactor. It's measured underneath the shield. And this is the counts per second counts per minute of neutron radiation coming off this thing. And we can see that if I turn my voltage down slightly, so I got my voltage control node down here, I'm dropping it slightly, you can see that my neutron output dipped. And that's because I'm not giving the reaction as much energy anymore. And without that much energy, I'm not going to get the same kind of radiation output from the reactor. One thing we can vary is the energy. And you saw how just by changing energy, I was able to change how that reaction worked a little bit. Well, another thing that changes that reaction is how much gas is present, right? Because that deuterium gas is what the reaction is occurring to. So I'm going to go ahead and I'm going to leave my voltage right where it's at. Or actually, I'm going to dial it in exactly. I'm going to set it right at 40,000 volts. And now, if I take my gas flow, which is this control right here, and I slightly increase my gas flow. Oh, I'm sorry, I'm in constant current mode. I didn't realize that. And they ever so slight. So I'm just going to enable the supply to go a little bit higher real quick. This is the whole thing about life science. There we go. So, let's see, where are we at? Okay. Sorry, gotta dial this in just a little bit. Okay, so you see, as I know, if I increase my gas flow, more gas, more current, and my neutron outputs come up again. So, but if my gas flow goes too high, we're gonna start wasting gas. And what will start to happen if I get too much gas, voltage starts to dip. So now we've realized that, okay, we've got two things we have to balance here, at least. We have to have the amount of gas in the reactor that has to be balanced with the amount of voltage or the amount of energy we can put in. Because, I mean, ideally, it's like, yeah, we want to take as much gas as possible and use as much voltage as possible to slam as many ions together as possible and get the most radiation. Well, you just assumed you had a perfect power supply. Welcome to the real world. We have constraints. This power supply can only do so much. So to maximize the amount of output this power supply can do, you've got to optimize your gas flow, and you've got to optimize how much gas is in the vessel. And there's two indicators of gas flow you can see. This one over here is how much is flowing into the reactor. This is through something called a mass flow controller. This is a really cool device. Like, you know, when you're let's say you have like a balloon, right? And you're letting gas out of the balloon. When you're letting that gas out of the balloon, it's not very precise. You can kind of just like open the end up a little bit, and it will let a certain amount out. And you can think of that like most valves. Like most valves, you turn open, and they just kind of let some amount out. The mass flow controller uses thermal mass of the gas to actually measure exactly how much gas is going into it. So it's a very precise device. I mean, like using temperature or something to see how much of it is there is really kind of cool. Right? So this mass flow controller is watching how much mass is flowing through it and giving us, and by converting the mass of gas to volume, we're able to get how many cc's to our reactor. So right now we're feeding it 4.6. I'm going to drop it down a little bit because that is a little bit much for the reaction currently. Let's see here. Okay. So yeah, I'm going to drop that down. Yeah, dropped it too far. It's a very touchy knob, in case you're wondering. And we'll just drop that down, current down, just to get stable. There we go. So let's think about this. The vacuum pumps on the scene are running at the same speed all the time, right now. I haven't touched the vacuum pumps at all. So if I change how much gas is going into the chamber, I'm also going to change what pressure I'm seeing right here. I'm just going to drop this current down a little bit more. So if I increase my gas flow, you'll see that... Oh, I decreased it there. So if I increase my gas flow, you'll see that my pressure starts to climb. So we've got the three things we need to balance now. We've got to balance how much gas is going in, how much gas is going out through vacuum, and how much energy we're giving the reaction. Sound good, right? Everything we need for a nuclear reaction right there. Kind of amazing. Let's see here. Let's take the reactor to a little bit different of a state now. I'm not producing very many at this point. So I'm just going to turn it down for a second. There we go. The chiller can't keep up with really long runs, so we gotta let it cool down just a little bit. So let's think about what's going on here. We've got these neutrons in this reactor, right? Remember how we were talking earlier about how the neutrons were coming off of the helium-3 reaction? Those neutrons are kind of interesting. They don't interact with very much. When they're going that quickly, when they come off of that reaction, they have 2.4 mega electron volts of energy. Mega electron volts is a measure of how much, simplified, is a measure of how much kinetic energy something has on an atomic scale. 2.4 mega electron volts is a lot of energy, and it's so much energy that the neutrons coming off this reactor, like, don't touch anything. They just, like, fly right by it. It's kind of hilarious. Not really the most useful thing in the world a lot of the time, but we can adjust that slightly. And the way we adjust that, or one of the ways we adjust that, is using, do I have an easily accessible chunk here? I don't. Wax. Simple candle wax. So candle wax has a lot of hydrogen in it. So let's think about what hydrogen is. What's hydrogen? One proton, right? Okay. You don't turn that off for now. Come on. So hydrogen is one proton. Neutron, one neutron. Neutron weighs exactly, or almost exactly the same as one proton. So we have all these hydrogen molecules in this paraffin. The neutrons that come off the reactor can actually impact hydrogen molecules in here. And this is really cool. Like, have you seen the Newton's cradle, right? Where you take the ball on one end, you lift it up, and it slings to the other side, and it looks like almost the same amount of energy is being transferred through each one of those masses. The reason that happens is because those masses are very, very similar. The most efficient transfer of energy happens between two objects of the same mass. That's why when you're playing pool and you have a ball, and so let's say you have a ball and you take another one and it strikes it, and that ball stopped moving and the other one took off in that direction, right? That's a very, very efficient transfer of energy, almost 100% transfer. The same thing applies to this reaction. The protons and neutrons coming out this reaction, when they hit those hydrogens that are stuck in some molecule, they transfer most of their energy into that hydrogen, and very, very effectively. So, and that hydrogen then, because it's bound, it's chemically bound to another molecule, takes that energy and it gets hit by it and it shakes around. And shaking on a subatomic scale is heat, right? What? There we go. And that, so we think about those vibrations, right? We're creating these vibrations. So we're just creating heat. So now we've taken a neutron. That neutron's hit a proton inside the wax. And for the energy of that neutron, most of the kinetic energy of that neutron into thermal energy of the wax. And so we've taken that 2.4 MeV neutron down quite a ways. And we create what's called a thermalized neutron. And so that thermalized neutron, we can now we interact with stuff because it's not going so crazy fast that it just bounces around. It'll actually do things. Let's bring this back up, see if I got my water temperature back where I need it to be. Yeah, we can run for a bit. Go ahead and turn our power supply back on. Let's turn our gas flow down a little bit. And start to bring our power supply back up. So I'm going to go to 5 milliamps on the dial. Slightly increase voltage. Just need to get this thing producing a little bit of neutrons real quick. Or not real quick, you don't want to be quick with this sort of thing. Turn my gas flow down some, let me increase voltage. Turn voltage up. So you see what I'm doing right now is I've got 5 milliamps of current flowing through this thing, but I'm not at the voltage I want. And the reason I'm not at the voltage I want is because there's so much gas in here that the gas is taking a lot of current, and the supply can't do that much. So when I turn the gas supply down, you can see voltage started to climb there, and now I'm imparting more energy per ion, and because each ion's got more energy now, I'm starting to produce radiation. So I'm going to go ahead and take this detector right here, and I'm going to reset it. No, that was the wrong 0. There we go. So you can see, when I have this tube right here, by the way, is a neutron detector. It picks up those neutrons. When I have this tube outside the reactor, or outside this block of wax, close to the reactor, I don't really get that many counts. Like, it's slowly increasing, but it's not really increasing that fast. And now when I take this tube, and I put it inside this block of paraffin, you can see that all of a sudden it's rising faster. I didn't move it that far. Like I didn't. The change in position is not what changed the radiation output. What changed the radiation output? The radiation output never changed. What changed was that this wax here is now taking those neutrons, those super fast neutrons that weren't touching anything before, not really touching or interacting with this detector, and by putting inside this wax now, we've changed the energy level of those neutrons, we've dropped that energy level down, and now they can interact with the detector. So you're seeing right here like a fundamental thing where we're taking kinetic energy and turning it into thermal energy and just doing it right here. And that's kind of amazing actually. So that's kind of one thing this reactor can do. So to make the neutrons more useful for things, we can use this paraffin wax to do that. And the other thing we have a lot of, if you move right here, is, so paraffin, it's wax, it's got a lot of hydrogen in it, right? What also has a lot of hydrogen in it? Water. So something you'll see pretty commonly used for neutron shielding is these water bricks. And these water bricks, think about water, it's got 1 oxygen, 2 hydrogen, that's from very, very dense hydrogen. And it's very, very useful for shielding. So you'll see a lot of nuclear reactor. At this point, the vast majority of nuclear reactors around the world use water bricks, or not water bricks, they use water. And that's because water is a really good neutron moderator. It does a lot of things. To make nuclear reactors work, like the big nuclear reactors that produce electricity, to make those work, you have to slow the neutrons down. The neutrons have to be able to create that chain reaction. They have to be able to hit that next atom of U-230 or of uranium to be able to make that reaction happen. So you fill the reactor with water, and that's what lets it happen. So now we've taken this reactor here, this research device we built in the garage here, and have this same exact concept going on here, same exact thing that's happening inside of the grid scale power reactors. So it allows you to do a lot of very, very interesting things. Let's see here. Is there any questions about anything we talked about? Or I know we kind of went over a lot from like the beginning of high voltage generation to what we can actually start to do with these neutrons and how we can start to change these neutrons. But it covers a lot of ground, but yeah. Well, with that, I'll go. Oh, yeah? Just talking to it?
Is water or wax more efficient at getting those neutrons?
By getting those neutrons, I'm guessing you mean thermalize those neutrons? Yeah. If memory serves, it's water. Although there are certain materials in certain cases where this will be more efficient depending on the energy level of the neutrons. What's more convenient is usually water because you can just store it in containers like this. The wax you have to like physically place in there. And when I was talking about those big grid scale nuclear reactors, the reason they use water is twofold. One, it slows the neutrons down. Two, it cools the reactor down. And it's actually, they use the same exact water they use to slow the neutrons down to transfer the thermal energy out of that core. Because remember, those neutrons, one of the things that produces heat inside the nuclear reactor, those neutrons hitting the water heats the water up. And that's part of what produces the steam that comes out of the reactor and spins the big turbines that produce the electricity. So the thermalization effect of the liquid is what does it. So it's used for more reasons than just it's good at blocking neutrons. It also cools it down. It lets you get the energy out of the reactor and a lot of stuff like that. Anything else? I'll go ahead and talk about one more piece of shielding on the reactor. When you think about like radiation shielding, you normally think about like lead, right? Like lead blocks radiation. It does. It blocks certain types of radiation. Lead barely touches neutrons. The neutrons from this reactor would pretty much, I mean, to some extent or another, go straight through lead. But they don't. And that's because the lead's a very, very big, has a very, very big nucleus. And that nucleus has so much mass that there's not an efficient transfer of energy from those neutrons to the lead, right? That it just kind of bounces right off. Because think about it. Remember how I had that pool ball example earlier? And how if you had one pool ball that hit another pool ball, that first one stops moving, the second one carries on? What happens when that pool ball hits the edge of the table? It bounces. It's the exact same thing that neutrons do off lead. They just bounce off of it. And it's like, whoop-de-doo, we're going to bounce, and it's not going to really do anything for us. So that is, but X-rays, different type of radiation entirely, or not different type, still, or, well, yeah, to a certain extent. Well, actually a very large extent. They're based off photons, not off of molecules, but the particle wave duality thing. But we'll get into that later. X-rays, very, very low mass, but their energy can be absorbed much better by the lead. And the energy being absorbed by the lead then stops the X-rays from carrying on. So that's why lead is used for X-ray shielding, but not for neutron shielding. In this particular reactor, we've got three main layers of radiation shielding. We've got our borated paraffin wax, we have cadmium plates, and we have lead. Now, the cadmium I haven't talked about yet. The cadmium does a really good job at is absorbing that last little bit of neutrons, those thermalized neutrons. Once they've been thermalized, well, they don't have enough energy really to be blocked by this paraffin anymore. But the cadmium then can absorb them of that energy, just because of the nature of cadmium. And so once they hit the cadmium, we cut it down quite a ways. Any other questions? Well, I think with that, we'll go ahead and end the show here and see what Carl wants to do. Nope. Just a second. Just keep going. Oh, keep going. Okay, cool. Let's see. What else have we got here in this reactor? What have we not gone over yet? Let's see here. I've got to turn this down again. Sorry, just got to manage thermal energy on this thing. So I think I talked a little bit about this earlier, but let's talk about the relationship between the voltage and current on this. So remember as I was bringing that thing up, I would just set the voltage somewhere, right, and just leave the voltage there. But it actually wasn't running at the voltage. Like, I have this dial set to 50,000 volts right now, but I've got no voltage running through this thing. And that's because this supply, instead of limiting voltage, limits something that is called a constant current supply instead of a constant voltage. So you see I have it in this mode right here. So constant current means that it will only output as much current as I let it. So as I start to increase this current, you see voltage starts to climb too, because you can't have any voltage without current, and you can't have any current without voltage. So if I turn one all the way down, the other one goes away. Now you can think of voltage as the water, as your water pressure, okay? And you can think of current as how much water there is. So let's take this thing. If I took the cap off of this thing, took the cap off it and poured it out, I'd have a lot of water flowing very, very quickly, right? But it wouldn't go very far. Like, it'd pretty much just fall straight down on the ground. So there's not much water pressure behind it. But if you take your garden hose is going to spray all the way across your yard. It's got a lot of pressure behind it. But it's not gonna move as much water as fast as me dumping this thing out is. So voltage and current are the exact same way. If I have a lot of voltage, I can go really far with it. But if I don't have very much current with that voltage, I'm not going to do much, because there's just not much, or there's not much actual electricity flowing. It really can flow, and it can flow really far, and it can flow really fast, but it can't flow very much. So by running this thing in constant current, I can adjust just the current side of this and see my voltage kind of follow that. Because as there's more current flowing through it, as I let more current flow through, I can get the voltage higher with that, okay? And I can do it the opposite way too. I'll take my current up to 5 milliamps. You see, as I start to drop my voltage, now I switch over to constant voltage, and now my voltage is what's limiting the current flow. Because if I don't have enough pressure to get across, to get across the reactor, kind of, to jump across this plasma, I can't carry that much current with me. Does that make sense? Just because, I mean, you got to have something to carry that current across. And in this case, the supply is the thing limiting this. Like, if this supply just ran away freely, it would go a lot higher than it is. But because I have the supply in this mode, I'm telling it you can only give it so much power, and that power can either be voltage or it can either be current, but it can't be both infinitely. That lets us it makes it easier to control the power supply. Previous power supplies, the power supply would just try to give it as much current as it constantly could all the time. That was interesting because the supply could only give 5 milliamps, but it would try to give more. And when it tried to give more, the supply had a nasty tendency of damaging itself quite significantly. If you remember a while ago, I showed you those electrical components that were just completely blown up by this thing. That's what happens when they gave too much current. There was too much water, we'll go back to the water metaphor, there's too much water flowing through them. So by this thing being a constant current supply, it will limit the amount of current and then start to drop voltage off to make sure that current doesn't go too high. So it makes it really easy to control. Because I can do something, so you see I got a plasma right now, I can turn the power supply off and turn it right back on, and it'll bring it right back to where it was. It's super duper easy to control. The old power supply was definitely not quite as easy and would consistently, you have to be very gentle with it. You have to really slowly ramp it up, really slowly ramp it down, and all sorts of stuff like that. Let's see here, what else have we got going on? Let's talk about what's going on the inside of the reactor right now. I'm going to turn the lights on inside the vessel. This may or may not work. Well, that worked to some extent. So you can see inside here, you got this thing coming down in the center, right? Or actually, yeah, we got this. Chloe, if we got the reactor vessel camera on the live stream, that'd be great. So we have this thing coming down the side of the center. You can see that little ring, right? In that ring, you see the plasma coming off of it, and you can see a bigger picture up there on the side. And that this ring right here is what's had, or I'll point this one. This ring right here is what has the high voltage applied to it. So that this high voltage power supply is connected directly to that ring and not the outer vessel. So what we've done is we create this very, very negative. Oh, there's buttons on that one. That is interesting. There we go. Just gonna turn this off for a second. So this ring has this high voltage potential on it, and that negative high voltage potential rips to ionize the gas. It rips the electrons off of it. Now, what charge does an electron have? Positive or negative? Negative charge. Okay. What charge does this thing have? And that by having that really high negative potential in the center, and then the walls at the walls of the chamber vessel at 0 volts. So we have, like, we'll say, just for example, negative 50,000 volts on one side, negative 0, or not 0 volts, because 0 can be negative, 0 volts on the other side. That really high potential field that's created literally just rips the electrons right off. Like, the electrons just go to ground. It's kind of cool that way. And when we take the electron off, so we have deuterium. It's got 1 proton, 1 neutron, 1 electron. If we take the electron off, we've changed the charge inside that deuterium. That deuterium is no longer neutrally charged, okay? So now if we take the negative electron off and we're left with the proton, what charge does the ion have now? Positive? Yeah, it have a positive charge. And so then that positive charge is attracted to the negative charge of the high voltage feed through. Just like magnets, right? Positive side of the magnet is attracted to the negative side of the magnet. It's the exact same thing with the electrostatic potentials in here. And as that deuterium ion gets attracted to the center, it accelerates. Just like if you have a magnet sitting on one side and you have a magnet over here, and you just kind of push it forwards, all of a sudden that magnet is going to get faster and faster and faster. I'm just going to move this real quick. There you go. That magnet is going to go faster and faster and faster towards the other magnet until it slams into it, right? It's the exact same thing that's happening here. Our ions are getting faster and faster and faster towards the center of the reactor to that poiser, and a bunch of other ions are doing the exact same thing, going faster and faster and faster to the center of the reactor, to that poiser in there. And the ions coming in together, they slam together, and boom, we have fusion. And it's a bit more complicated in this one, because you see that we have that, if I turn the light off again, we have that shaft of light, right? That shaft is the ionized deuterium in there, but it's not exactly towards the center, and that's because of the shape of the reactor. Now, think about my earlier example where I had 0 over here, right, and negative 50,000 over here. Now, what if instead of that, I had negative 50,000 right here, and I had 0 volts surrounding it in a big circle, right? So all of a sudden now, if we have ions anywhere inside that cloud, they're all going to travel to the center. Now, they're all going to travel at the same rate, right? Because it's a circle, so it's very, very even. Now if I took that negative 50,000, I put that in the center again, but this time I draw a square from my 0 volts. Now I have this 0 volt square potential surrounding that negative 50,000 volts. Well, let's think about this. If I go straight up to the top of that square, right, that's a very short distance. But as I start to, if I go straight up and over to a corner of the square, all of a sudden I have a lot more distance. So my field, they're known as electropotential field lines or equipotential lines. So if I draw these lines of in between, so the field line that's in between 50,000 volts and 0 volts is 25,000 volts. So if I draw the point at which I'm equally between the two of those, for a circle, that's just a smaller circle inside. It's very consistent. For a square, though, it's kind of rounded at the corners now. And it is still squarish, but it's also very rounded. And that's just how the distance function works out. And so that those equipotential lines define the shape of the plasma. So let's think about a reactor. You've all seen the reactor before. It's the vessel. It's got like the six pieces coming out of it, right? But primarily our beams traveling between two of those. So what's going on is that those field lines create a cylindrical formation. Because remember, we've got a cylindrical reactor, right? Cylindrical pieces coming out of the reactor. Those field lines create that cylindrical formation of the plasma. And that's what defines our plasma shape. So the acceleration isn't just happening in the center here. It's happening all over that plasma. And we're getting that ion formation all over that plasma. And so that we can go more into field lines too. Like we can really, really go into field lines for a really, really long time, and it gets really interesting. But those field lines are fundamentally what define the shape of the plasma in the reactor. And remember that plasma, that ionized gas, is where the fusion is happening, so it also defines where the fusion is happening. Any questions? Okay. So something else that's kind of interesting that happens, let's talk about this. So remember how the reactor has got that six-way shape, right? You only see the plasma from one direction and from a side, and it looks like it's going straight between the two, right? In reality, that plasma is shaped like a diamond with 4 points. Does anyone want to guess where those 4 points come from? Think about those field lines. Think about what shapes those field lines, and think about the shape of the reactor. Here, you can pass it around. So those field lines are defined by the reactor vessel geometry. And in addition to the field lines that create that cylinder back and forth, we also have those 4 cylinders that are coming off the sides of the reactor, right? And those 4 cylinders coming off the sides then define that diamond shape that you see on there. Like those field lines that are way back in the center of the reactor carry over to the very end of the reactor and give us those really interesting shapes on the conflat. So you feel like you know a lot more about what's going on the inside of the reactor, like it's not as much as a black box anymore? Are you ready to try and make a reaction happen yourself? Ready? Okay. So I'm going to go ahead and zero this out. I'm going to shut the power supply off. I'm going to turn my gas flow down. So I've got my gas flows all the way down. My pressure's dropping to 0. I've got no voltage happening. My current is set to 0. And my voltage is set to 0. And we want to get a reaction happening out of this thing. So what do we need to do here? We got to balance 3 things, right? We got to balance gas, we got to balance voltage, and we got to balance pressure. In this case, and we got to balance vacuum. In this case, we're not going to touch vacuum because I know vacuum is set correctly, and the control is behind that cabinet. I don't want to access it right now. So we're just going to leave vacuum alone. So what we have left is we have to balance gas, and we've got to balance voltage and power. So who wants to turn the high voltage on? Cool, let's do this. So go ahead and turn high voltage on. So to start, you press the green button. That enables it, and then you can press the red button, and that will turn it on all the way. But when we turn high voltage on, nothing's happening still, because I got my dial set all the way to 0. We're just going to ignite a plasma for now. We're not going to do anything fancy. So what we'll start out with is, you want to come up here and do this? So what we're going to do is we're going to take this dial right here, and you see as we turn it, we have the smaller numbers on the inside, and then as I go past a certain point, the number on top clicks over. Yeah. So that's 1, 0, or 10, so 10,000 volts. So I'm going to go ahead and have you do is I'm going to have you dial in 20,000 volts on there. So you're going to go past 1, and then you're right, oh, you're at 2. So you go to 2, 0. So 2, and then 0 on there. And now we're at 20,000 volts. So we got the voltage now. And you want to go here? You want to come up and do this part? So now we have voltage, but we don't have any current, and our current still is 0. So let's go ahead and we're just going to dial in 5 milliamps for now. In this case, it's the big number up here. That's how many milliamps it is, and that's point whatever is on the smaller dial. So we turn this to the right. You'll see how it jumps over to 1 like that, right? So I'm going to go ahead and have you set in 5 milliamps on the dial. You can go pretty fast. Just stop at 5. Okay, so we got 5, 0 there. So if you want to go back there, so this is kind of interesting. My maximum current set at 5 milliamps, and my maximum voltage is set at 20,000 volts. And you see, I'm at 20,000 volts, but I've got no current. Anyone want to tell me why I have no current? I have nothing for the voltage to travel through. I don't have any gas yet. So the voltage can't travel across an empty vacuum. There's nothing for it to traverse across. We have to get the gas there for that voltage to travel across in order to get that current. So do you want to come turn our gas flow up? So this is our gas flow right here. I've got it set to 0. I'm going to have you really slowly start to increase this. And while you're really slowly increasing this, I want you to watch what happens to your current meter, okay? So we're on the number 2 controller, so go ahead and slowly increase that. So turn it to the right. Yep. Okay, you can slow down a little bit. So you see, as we turn it up now, up. So we turn it just a little bit more. You see more gas, more ions in this, and more current traveling across it. So now we've started to see like how we're able to balance this out, right? Yeah.
So what do the 4 dials do? Like what's the 1, 2, 3, 4?
So this reactor is configured to be able to supply multiple gases simultaneously to the reactor vessel. So our controller can control 4 of those mass flow controllers simultaneously. I'm only using controller number 2 right now because I'm only flowing deuterium gas into the vessel. In reality, I only have 3 working controllers on the instrument right now, and only one of them is even plumbed into something. So if I open one of the other ones up, I'd just be letting the air into it. And yeah, you can do stuff with that, but it doesn't produce fusion. So yeah. So we got our gas flow up, and go ahead and turn this up. So remember, you set it to what? How much current? 5 what? 5 milliamps. So let's go ahead and turn that up until we hit 5 milliamps. Right there. Perfect. Dead on. And we just got to be close, okay? So here, let's see. You want to come up here and do this next step? So you can head back to your seat. So, let's think about this. When I was running earlier, we were getting nuclear events were happening, right? But I've got no neutrons, or just about no neutrons being produced right now, because I just don't have enough energy being imparted on my ions. My ions are not moving fast enough to fuse together yet. And what enables the ions to move fast enough to fuse together is how much voltage there is. So you see, I'm only at 20,000 volts because I've got it limited at 20,000 volts. So go ahead and take that dial, and let's go to 30,000. So get 3 on the 0, or get 3 on the top and 0 on the bottom. So that's interesting. That didn't move at all, right? That stayed almost exactly the same. And the reason it stayed the same is I have 5 milliamps going through this thing right now, and the supply is set to not do any more than 5 milliamps. But if I slowly start to decrease my gas, so turn this to the left a little bit. Sorry, to the right. You see, as I decrease my gas flow. Oh, sorry, I'm very confused. Yeah, definitely to the left. I'm like facing this direction, trying to control that direction. It's not going very well. So slowly start to decrease that. You can see now that as I decrease it, I'm able to get more voltage going through it, right? Because I have less gas. Less gas, same current, means more voltage. And now we've maxed out at 30,000 volts, so we got into constant voltage mode, and the supply's holding it right there. So what we've done now is you're still supplying that 5 milliamps to the gas. But because there's less gas, we're able to give it more voltage, and we're able to accelerate the fewer gas ions left to a higher energy. And by imparting that higher energy on it, we're able to get closer to producing nuclear fusion. Sound good? So you want to come to the next step? So you can see here, we've got a little bit of neutrons being produced here right now, about, I don't know if that one's calibrated correctly, but according to this, we're getting 1,500 counts per minute right now, neutrons. We're at 30,000 volts, 5 milliamps, 1,500 counts per minute on the inside of this reactor. So if you want to come down here, and let's go ahead, we're going to set our voltage. We're going to set to 50,000 volts, so 50. So go ahead and set the voltage again. So we're at 50. And you can see our current's still at 5 milliamps, and our voltage is still at 30,000 volts. But all of a sudden, we've got no change. It's doing the exact same thing. We're letting it give it more voltage, but it's not able to put more voltage in. Why is that? What? Current stayed the same. Why did current stay the same? Because the supply told it to. But why is that current so high? Because of our gas. The gas is what determines how much current can flow through it. And if I'm getting 5 milliamps at only 30,000 volts, it's going to stop at 30,000 volts. If I just turn my gas down a tiny bit, see, all of a sudden my voltage climbs. Because now I've got less gas molecules, same amount of current, means a higher voltage. There's an equation that gives you a relationship between voltage, current, and its resistance. Resistance varies by how much gas there is. But by changing the amount of gas, we can change the amount of gas, maintaining constant current. We can supply more voltage, more accelerating potential to each individual ion. And you can see our neutron output has slightly decreased because this reactor can be a pain sometimes. Oh, actually, no, sorry. It's exponentially increased. There's an extra 0 on the end of it. We're actually at 100,000 counts per second now instead of only 1,500 counts per second. Or instead of instead of 15,000 counts per second, we're at 100,000 counts per second. So that's a quite dramatic increase. And we increase our neutron output by decreasing the amount of gas flowing into the reactor, which is kind of a weird relationship. Less gas, same current, more voltage, more neutrons. So we can keep doing that for a while. Actually, we can keep dropping our gas, increasing our voltage, more neutrons. Dropping our gas, increasing our voltage, more neutrons. And at that point, we enter into kind of an engineering design constraint of our reactor. We really can't give it more than 80,000 volts. You might be able to sneak a little bit more out. We don't want to. We don't have the. When you get up to that range, you need bigger power supplies. You need more insulation, and we just don't have that. So we don't take it beyond. We don't, and we also can't take it beyond 80. It is a 100,000 volt power supply. That is true. But I have a resistor back there that drops that voltage down through a phenomenon known as voltage drop that we'll go over as we get into more details on how electronics work. But that's a bit more involved than we're going to do right now. Yeah?
So essentially what you're saying is to have fusion go on in the reaction, there are 4 manipulated variables, and without the 4, fusion wouldn't occur, right?
Yeah, fusion wouldn't occur in this method. This isn't the only way of achieving fusion. This reactor accelerates the ions, slams them together, produces fusion. There's other ways of getting the ions together to have fusion occur. One of which is the biggest fusion reactor in our solar system. Anybody have a guess what the biggest fusion reactor in the solar system is? The sun, exactly. Now the sun doesn't have a high voltage power supply. And yeah, there's a lot of high voltage around the sun for a variety of other reasons. But that's not what produces fusion. The sun's just big enough that it's got enough gravity that instead of having to use the voltage to slam those ions together, the sun just like forces the ions together and fuses them together, which is kind of insane. Like it's just like we're just gonna crunch really hard on this and we're gonna make stuff. And that's how the sun does fusion. You can also do fusion using magnetic confinement, where you ionize the gas, and yeah, you do have to use a high voltage to ionize the gas, but Then you use magnets to manipulate the gas to compress the gas together. And that's another way of producing fusion. Yet another way of producing fusion. This was going to sound really crazy, but there's actually an entire company in British Columbia working on this. They take the gas, the deuterium, they ionize it, and they inject it into the center of the reactor. And their reactor isn't anything like ours at all, okay? It's not this vacuum chamber with electricity on top and walls all around it. No, it's a spinning pile of liquid lead. It's a lead vortex they have. Like hundreds and hundreds of pounds of molten lead. Like that's crazy. It's insane. Who does that? Well, General Fusion does. And so they take the gas, they inject it into the center of this, in the center of the spinning lead, and then from every side of the lead, they have these big pistons come slam into the lead. And when it slams into the lead, that vortex in the center collapses. And that collapsing vortex increases the pressure of the gas, of the ionized gas, or it doesn't even have to be ionized, honestly. The gas in the center of it to such a point that the gas ions, or the gas, doesn't have to, as I said, doesn't even have to be ionized, just slams together and fuses together and produces a bunch of heat. So the idea is that, okay, you're producing this heat in the center of this liquid lead, and that heat produced in that reaction keeps the lead liquefied, and then over time, you can take a little bit of the thermal energy off of this reaction. And with that thermal energy you're taking off, you can produce steam, you can spin a turbine, you can spin a generator, and you can produce power for the electrical grid. So I mean, there's a lot of different ways of achieving fusion. This is just the one we did here. Anything else? I can keep talking about other systems on the reactor if you're interested in it. Turn that off for now. Just, well, let's see here.
Specifically for our reactor, is there an equation that models the amount of neutrons outputted by the reactor based on the gas, or the amount of gas, the voltage, the pressure, the various manipulated variables you have?
You just assumed an ideal world. If this reactor were 100% ideal, yes, there is an equation. I can determine how much energy I'm putting into each ion, the probability of fusion based on the nuclear cross-sections, and a whole bunch of other things, and give you a number. But welcome to the real world. The reactor is not perfect, and it's not perfect in one kind of interesting way. Its vacuum is not perfect. Its vacuum is not made of just deuterium, right? There's a little bit of other stuff in that vacuum too, and the other stuff can poison the reaction because you're wasting energy on non-deuterium ions inside the reactor. So when we turn the reactor on, remember how we were doing like vacuum work last week? How I was talking about outgassing from the reactor, how the water vapor that's on the surface of the metal can outgas? That happens a lot in this reactor. So when we first start the reactor up, and we ignite that plasma for the first time, well, all of a sudden that high energy plasma that's fusing together is also slamming into the walls of the reactor. When it slams into the walls of the reactor, it releases that water vapor, and the water vapor becomes oxygen and hydrogen. And oxygen and hydrogen don't fuse in that reaction. So all of a sudden you got these oxygen ions, these hydrogen ions, and the deuterium ions floating around. But those oxygen and hydrogen ions are stealing energy that could be used with the deuterium reaction and just stealing it and ionizing themselves, but not actually reacting. And that's just one of the variables that affects how much fusion there is. That's not as easily controlled. And that effect does decrease over time. The way you'll notice it is that for a certain gas flow, you'll have a certain pressure. Like I have my gas flow set to 3.6 cc's right now. If I drop my gas flow down to, we'll go to 5 cc's, you'll see eventually my pressure is going to stabilize. So we're going to about 18. And as soon as I drop back down to 3.6, just doing it really carefully because I do want to hit 3.6. As soon as I'm at 3.6, I'm back at 0.013 torr. So there is a relationship between that. But when the chamber is outgassing, this number will be higher. Because, yeah, I am giving it a certain amount of gas, but because of the outgassing the walls, that pressure will be higher than it is right now. And that's really, really noticeable when you're first running the reactor, and not as noticeable later on, but it does affect it still, to some extent. So that's one thing that's harder to model. And you can always make an equation for something. Like you can throw as many multipliers on as much algebra on, and you can eventually get an equation that will probably be close. The question is whether or not that equation is really useful. So from a purely theoretical point, modeling this reactor is challenging, but possible. So, yeah. Let's see here. What else do we want to talk about in the reactor? Do I have any of this out? I'm going to see if I have a certain part over there real quick. Let's see here. Is this one of those parts? No, it is not. Okay. So remember I told you earlier that the fusion occurs in between the ions inside the reactor? I'm sorry, I might have lied to you a little bit there. I didn't actually lie to you, I just didn't give you the whole truth. The fusion doesn't just happen in between the ions inside of the reactor. The fusion also happens in between the reactor, the ions inside the reactor, and the wall of the reactor. Well, hang on, the wall doesn't have any deuterium in it. No, it does actually. Just like the water vapor can be implanted into the walls of the reactor, the deuterium can too. So that beam of plasma you see there, right? That beam of plasma is hitting the ends of the reactor. If it weren't hitting the ends, you wouldn't get that shape. But that beam is that beam is actually the ions are going very fast inside that. So the ions actually get slammed into the end of the reactor, these end plates, so quickly that they implant themselves into these end plates. So all of a sudden, you got atoms of deuterium stuck inside the end plates of the reactor. And then, when you have atoms of deuterium that are stuck inside the end plates of the reactor, and then you have more ions of deuterium that come and slam into the end plates of the reactor, sometimes those ions that slam into the end plate will hit deuterium that's already there with so much force that it'll fuse again, and you'll get a fusion event on the end of the reactor, like inside the wall. So that's known as beam-on-target fusion. You're slamming a beam of ions into a target, and that target and there's fusion events happening inside that target. So the deuterium ions don't stick very well in just stainless steel. They do to some extent, and it is an effect that happens, but just barely, really. However, due to the material properties of titanium, titanium will absorb hydrogen much, much better than stainless steel will. So there's more hydrogen absorbed in titanium. So what we've done is we've taken pieces like this. This actually used to be in the reactor, and we bolted a piece of titanium to it. So now our beam's not hitting the stainless steel. Our beam's hitting that titanium. And that titanium effectively acts as a hydrogen sponge and just holds the ions in place for the beam to come hit. It still takes the exact same amount of energy to do it. It's just increasing the number of ions that can actually undergo collision. The number, not ions, the amount of deuterium that can undergo collision. And that's known as a cross-section. A cross-section is a variable used to define how much something can happen to it. And the reason I say something is that can be fusion events, that can be how much radiation is blocked. Cross-section is used for a lot of things. In this case, we're using cross-section to define how much deuterium is in the beam line, what cross-section deuterium can I hit with it. So that's another place that fusion happens inside the reactor. Let's see. Any other questions? So we've got the two types of fusion that occur. We have the beam-on-beam fusion, and we have the beam-on-target fusion. And depending on how we're running the reactor, we can change how much of the fusion is made up by any one of those things. By how much fusion occurs in beam-on-beam, and how much occurs in beam-on-target. Let's see here. What else can I want to show you? I'll show you a cool radiation monitoring device. Yeah, I got one over here. So this detector right here is called a helium-3 detector. And what it has in it is it's got a piece of wire suspended in that helium. And it's got a, how many volts is this? I don't even know how many volts this one is. And basically, using a really skinny piece of wire, we can detect neutrons hitting the helium and hitting the wire itself around it. And so by just being able to really accurately amplify any effects that happen to that piece of wire, we're able to count the number of neutrons that strike it. And this is a little bit simplified, but we're able to count the number of neutrons that strike it and record it here. So that relies on electronics, it relies on circuitry, relies on a lot of stuff to make happen. But what if there's a chemical way of doing it? And there is. And that's known as a bubble tube. We use bubbles to detect neutrons. It's kind of fun. So this bubble tube has a special gel on it that the exact formulation of which is a very closely guarded secret by the company who makes this. But when neutrons interact with the gel inside this thing, the neutron causes a chemical reaction at a very determined rate, and that chemical reaction forms a little bubble of gas. And so this one's used up, or not used up, it's just it's worn out, so it won't work anymore. The bubbles won't reset. But each of those bubbles inside it, and I can pass this around, each bubble is equivalent to a certain amount of radiation. If I can see this real quick, let's see here. One bubble. So yeah, so 36 bubbles equals 1 millirem of radiation. So if you count 36 bubbles in this tube, you know that this tube was exposed to 1 millirem of radiation. And a rem is a unit of measurement of radiation, just like a milliliter is a unit of measurement for liquid. So that's, or like a liter is a unit of measurement for liquid. So by using these bubble tubes, we can put this in different places and record how much radiation has struck them. So it's just another way of detecting neutrons. And I've got one more way of detecting neutrons, because you can never have enough way of detecting neutrons, right? Like, where's the fun in that? And that's this thing right here. This is, its name's Priscilla. It's a proton recoil detector. Basically, what happens inside of this detector is the neutron comes in, and there's a special material in there that when it gets hit by a neutron, scintillates. It produces a proton, produces something with a charge. And that thing with a charge, because the proton has a charge, right, has a proton carry currents, that charge is detected by the counter right here. So this thing basically counts the number of protons that are freed by the neutrons that strike the detector and gives us an output. And that's a very, very accurate way of measuring neutron output, much, much more accurate than the helium-3 tubes. And it just gives you a count. It tells you how many are coming out, how many neutrons are coming out, and it's just great for that. Now, the helium-3 tube is interesting. Remember I was talking about the energy levels of the neutrons earlier? Right? How you can have like the 2.4 MeV neutrons that come off of it, you thermalize them and change the energy level. Well, the 2.4 MeV neutron only comes off of the deuterium to deuterium reaction. There is different energy levels of neutrons that comes off of different nuclear reactions. And the different energy level of neutron interacts with those helium-3 detectors differently. So a higher energy neutron will have a different interaction with the detector than a lower energy neutron. And you can record those different interactions and actually create a spectrum of the energies coming off of a reaction. So if I look at the spectrum of this reactor right here, I'm going to see two very strong peaks. I'm going to see one peak that is the deuterium. It's going to be at 2.4 mega electron volts. And I'm going to see a second peak that is the thermalized neutron that come off that. And that's going to be really close to zero. It's a really tall peak around zero. There's a lot that comes off. So this will be over here. So there's a really tall peak around zero. A lot of neutrons coming off of it. Kind of a gully right here. And then a peak around 2.4 mega electron volts. And that's the spectrum of the radiation that comes off this reactor. You could think of the spectrum just like you do think of the spectrum of light, right? Light's got a bunch of different colors in it. Each color is a different energy level of light. And you can record how much of each energy level of light's interacting with something. In this case, we're recording the energy level of the neutrons. So if I had a different reaction going on inside this reactor vessel, I would get a different energy level, a different energy level of neutrons coming out of it. And I'd be able to detect that different energy level with the spectroscopy, with the helium-3 spectroscopy equipment. So this particular counter right here does not do spectroscopy at all. Like you see, it gives you a number, right? It doesn't tell you what the different energy level is. However, the computer station over there, that does give us that information. So if Chloe, if you want to, okay. So next week we'll talk more about spectroscopy, and I get you over to the spectroscopy station, and we'll be able to kind of actually see like, oh yeah, there's the 2.4 MeV neutrons, and there's all the thermalized neutrons, and you can change how much that there is by moving detectors around. But our spectroscopy detector is actually underneath the shield, and well, I have a nuclear reaction going on underneath the shield, so I can't exactly lift the shield up right now. Like that wouldn't be good for anybody. In fact, if I lifted the shield up right now, the power supply would automatically shut off because there's an interlock that won't let the shield be lifted with the power supply running. So real quick, any final questions? Yeah?
So you know when you said about the bubbles in this
Yeah.
thing? So you know how sometimes there is bubbles in water? I mean, there's a neutron or
No, no, not at all. There's a very specific chemical inside this tube, and that very specific chemical is sensitive to neutrons. And it only undergoes its chemical reaction to form that bubble when a neutron is present. This isn't just water, though. This is a very expensive, very specialized gel that I have no clue what's in it because the manufacturer doesn't want anyone to know what's in it, so they can be the only one who sells it. So yeah, there is neutrons in water because there's neutrons in the atoms, but there's not free neutrons floating around like there is at this reactor here. Any other questions? Yeah?
What type of radiation does the reactor create?
Yeah, so the reactor primarily creates two types of radiation. It creates neutron radiation and it creates X-rays. Those are the types of radiation that actually exit the reactor vessel. There's a lot more types of radiation that are created inside the reactor vessel, one of which is light. Light's a radiation, and light's given off by this reaction just because the ions are so fast. And remember, kinetic energy is thermal energy, right? So really fast ions means they're moving, means that they're really hot. And when things get really hot, they glow, right? Like the light bulb, old tungsten light bulb, it gets really hot, it glows. It's the same thing going on inside the reactor. It gets really hot, the plasma glows. So we have light coming off of it. We also have one more type of radiation. Just like we have neutrons coming off, we have protons coming off. The thing about protons is, protons don't travel through barely anything. As soon as they touch the metal, protons absorbed by the metal. So neutrons travel through the metal, protons don't. So you don't get any protons leaving the reactor vessel. You only get the neutrons leaving the reactor vessel. And the X-rays too. And the X-rays are just a result of there being so much electricity and so much energy around that the electrons in those ions are jumping up and down. And that jumping up and down in energy levels, when the electron falls back down in energy level, that's when the X-ray is given off. So yeah, more than a couple different types coming off this thing. And we have other detectors for those other types of radiation. Like over there on the right-hand side is our X-ray detecting equipment. I have two lines over here. I have one line that's X-rays and one line that's neutrons. Well, the bottom line is the X-ray detector. Unlike neutrons, no X-rays escape the shield, so I can take an X-ray detector and wave it around the outside of the shield, and I wouldn't get any counts because the lead inside the shield is very, very effective at stopping those X-rays. Anything else? Well, with that, I'm going to go ahead and call that a show. Hope you all learned a lot, both here and online. Please tune in next week, and we will be going over another very interesting topic.